It is a world of crushing pressure and absolute darkness, yet through it runs a ribbon of light and steel. Here, millions of tons of seawater hang suspended just meters above, held back by a seamless fusion of concrete and engineering, assembled with a precision that borders on the microscopic. This journey, seemingly torn from the pages of science fiction, is a testament to modern ingenuity. It is the reality of the underwater tunnel, a true triumph of human ambition. The question, however, is how such colossal structures are even possible. How can we build in the face of immense water pressure, contend with shifting, unstable sediments, and operate in an environment utterly cut off from the world above? The answers lie deep beneath the waves, where humanity has learned to turn the impossible into breathtaking reality. Beneath the crushing weight of the ocean, a new world of connection is forged. These monumental passages are more than just engineering marvels. They are the lifelines reshaping global infrastructure and expanding the reach of human connection. Stretching beneath vast oceans, mighty rivers, and deep bays, they unite lands once separated by water, igniting a quiet revolution in transportation and logistics. Journeys that once required ferries or towering bridges are now completed in mere minutes as travelers move seamlessly from one island to the next, or cross a wide bay deep below the surface. But their impact extends far beyond convenience. These submerged corridors sustain the global flow of goods and people, ensuring commerce moves swiftly, securely, and with remarkable efficiency. For many nations, particularly those with bustling port cities, these tunnels have become vital arteries of economic growth, unlocking new avenues for regional development and global trade. The journey to create such a structure begins with exhaustive preparation and a demand for near-perfect precision. Every step is meticulously calculated to guarantee the project's safety and ultimate feasibility. The initial phase unfolds on the ocean floor with comprehensive seabed surveys. Engineers meticulously map the subsea topography, gathering soil samples and analyzing rock strata to reveal the underlying geology. This deep analysis determines the stability of the seabed and uncovers any latent hazards that might compromise construction. Alongside the technical work, environmental stewardship remains a guiding principle. The project team must carefully assess the tunnel's potential effects on marine ecosystems, ensuring that native species are protected and their natural habitats remain as undisturbed as possible. To honor this commitment, noise mitigation measures are often employed during construction, and in some cases, artificial reef structures are installed to foster new habitats for marine life. On solid ground, a colossal structure takes shape, destined for a world without light or air. With the seabed now mapped, the true work of construction can begin, often relying on one of the most trusted techniques, the immersed tube method. The process unfolds not in the water, but on land, where enormous segments of reinforced concrete are prefabricated. Each standard element stretches an astonishing 217 meters and carries the weight of over 73,000 tons. These sections are crafted with meticulous precision, designed to align perfectly and form a watertight seal once submerged beneath the waves. Inside their hollow forms, dedicated compartments await their future purpose. Two vast chambers are reserved for highway traffic, another for a railway line, and a separate service corridor is carved out for future maintenance and inspection. When fabrication is complete, these behemoths are guided out to sea, where floating pontoons and specialized cranes begin the delicate task of lowering them into a pre-dredged trench on the ocean floor. One by one, each segment is carefully joined to the next, slowly forming a continuous passage of the required length. The most critical phase of this entire operation lies in these connections, where even the slightest imprecision could invite the crushing force of the sea. To prevent seawater infiltration, heavy rubber gaskets are fitted between the segments, while layers of sand and gravel are carefully placed above and around the structure, anchoring it against the buoyant pressure of the water. Only when the connections are securely locked and stabilized are the temporary bulkheads at each end removed. This final step transforms the individual tubes into a single, seamless, and watertight tunnel. Yet this remarkable technique is only viable where the seabed is stable and the currents are gentle. In environments with strong turbulence or complex underwater terrain, The challenges of anchoring the segments and maintaining their integrity make the immersed tube method entirely impractical. It is a subterranean factory on the move, a city block of steel grinding its way through the dark. Where pipe lowering is not an option, engineers turn to the shield digging method, a technique embodied by the tunnel boring machine. This colossal system operates as a self-contained world, capable of excavating soil, removing debris, and installing reinforced concrete linings all in one continuous, closed-loop process. This allows for uninterrupted construction deep beneath the earth or riverbeds, all while maintaining precision, safety, and minimal surface disruption. At the very front of this mechanical leviathan lies a massive cutter head, a spinning disc of steel nearly 12 meters in diameter and weighing over 200 tons. It is armed with 140 high-strength cutting discs and blades, turning at a deliberate pace of approximately 2.7 revolutions per minute. As it rotates, the cutter head exerts a crushing force of up to 400 bar, enough to pulverize even compact rock and dense soil. The excavated material is immediately drawn into a chamber directly behind the spinning face. Here, foam and water are injected to maintain a delicate earth pressure balance, a critical step that prevents collapse in soft or water-saturated ground. This slurry mixture is then carried away on a continuous conveyor belt, traveling all the way to the surface where it passes through a discharge tower. Lime is mixed in to reduce moisture before the processed earth is loaded onto trucks for disposal. Meanwhile, as the machine inches forward, its rear section automatically installs precast concrete segments, forming the permanent tunnel lining. Once a full ring is assembled, a specialized grout injection system fills the void between the new lining and the surrounding soil, securing the structure and ensuring it remains completely watertight. Hydraulic cylinders then push the entire machine forward, beginning the next cycle of excavation and installation. Each cycle takes roughly 90 minutes, allowing the team to complete 8 to 10 lining rings per day, which translates to about 20 meters of finished tunnel. Operating around the clock, hundreds of engineers meticulously monitor pressure, temperature, power systems, and real-time camera feeds to maintain perfect stability. Thanks to its sealed and automated design, the TBM can operate for months without interruption, a true symbol of modern engineering. Its only significant limitation is speed. When it encounters extremely hard rock or unpredictable pressure zones, engineers must halt the process, extract the machine, and switch to alternative methods to safely continue their work. When faced with geology that can shatter steel, engineers turn to a more primal force. This is the drill and blast method, a raw yet precise technique reserved for the planet's hardest rock, where modern machines simply cannot advance. The work unfolds not in a continuous grind, but in a meticulously choreographed cycle. It is a sequence of drilling, blasting, clearing debris, and then reinforcing the newly exposed earth, demanding unwavering precision and a strict adherence to safety. The process begins as dozens of blast holes are bored into the tunnel face, following a pattern laid out in technical blueprints. Into each borehole, cartridges of explosives are carefully inserted, each one fitted with an electric detonator. These are all linked by detonating cords, arranged in specific groups to govern the exact sequence of the explosion. Every detonator is timed with immense care, designed to optimize rock fragmentation while minimizing the resulting vibrations and their impact on the surface far above. Before any material is brought underground, it is scanned, tested, and certified as safe. As preparations intensify, massive ventilation fans and air ducts are disconnected and depressurized, a crucial step to prevent the shock wave from ripping the ventilation system apart. Just before the blast, crews measure the circuit's resistance and perform a final, thorough inspection of every connection. Only when every single safety condition is verified can the command be given. Electrical signals race through the network, triggering the detonators and shattering approximately 1.5 meters of solid rock from the tunnel face. Following each blast, all work ceases for at least 20 minutes, allowing for crucial inspections and for the air to be cleared. On an average day, each blast consumes between 80 and 100 kilograms of explosives. With 9 to 18 such detonations occurring daily, the frequency dictated by the geology and the project's scale. While this method can offer faster progress at a lower cost, its intense vibrations can crack nearby structures and cause water leakage, making it entirely unsuitable for underwater tunnels where shock waves would also devastate marine life. For these reasons, the drill and blast technique is reserved almost exclusively for mountain tunnels and dry ground excavation, in places where other methods are simply not an option. When the Earth itself refuses to yield and the sea presses in from all sides, engineers must turn to the oldest methods of all. In geological conditions too treacherous for massive boring machines, or where immense water pressure makes other techniques impractical, traditional excavation becomes the final, formidable option. The process begins with the construction of a main vertical shaft, plunging from the surface deep down to the tunnel level. This shaft becomes the artery for the entire project, a conduit for workers, machinery, and materials moving in, and for excavated debris moving out. Crews drill into soil and rock, loading the spoils into sealed containers that are hoisted to the surface by crane for processing. In zones where blasting is forbidden or the ground is too fragile, they shift to hydraulic cutting tools, meticulously slicing through the sediment layers. Though a slower technique, it critically reduces the risk of ground settlement and preserves the tunnel's integrity. After each phase of digging, the newly exposed earth is immediately sealed with a layer of shotcrete. This is followed by the installation of heavy steel arches, mesh reinforcements, rock bolts, and anchors, a layered defense against the immense pressure waiting to reclaim the space. Around the clock, mechanical and maintenance teams monitor air pressure, equipment integrity, and the vital dewatering systems. The most critical factor is maintaining a perfect equilibrium between the tunnel's interior and the surrounding environment. Any imbalance could invite the sea to infiltrate, flooding entire sections in an instant. By merging classical engineering principles with modern monitoring, this method remains a trusted solution for the most complex underwater projects. It is here, beneath the ocean, that only persistence, precision, and a deep understanding of marine pressure can guarantee a structure's survival. The final section is lowered, the water stills, but the true test of endurance has only just begun. Before a single vehicle can pass through, the structure must prove its safety in a rigorous operational assessment. Many of these modern marvels are designed with two distinct levels: a clever solution that doubles traffic capacity without widening the tunnel's footprint in the delicate seabed. Inside, vehicles will move at a steady 60 kilometers per hour, with emergency exits placed every 200 meters for immediate access. Once construction is complete, engineers subject the tunnel to a gauntlet of trials. They test its waterproofing against immense pressure, its resistance to fire, and the performance of its complex heating and ventilation systems. The overall stability of the entire structure is scrutinized through a relentless series of evaluations, ensuring every component can withstand the forces of the deep. The journey of an underwater tunnel, however, doesn't end when it opens to the public. Its true lifespan is measured not in concrete and steel, but in constant vigilance. Dedicated technical teams conduct methodical inspections, examining the concrete lining, waterproof membranes, support frames, and drainage systems for the slightest sign of deformation or cracking over time. An invisible network of guardians stands watch. Hundreds of sensors embedded along the tunnel act as a nervous system, continuously monitoring pressure, temperature, humidity, and vibration. This stream of real-time data flows to a central control room, allowing engineers to detect the earliest whispers of structural fatigue. Meanwhile, specialized vehicles equipped with high-pressure water jets and powerful suction systems periodically cleanse the tunnel, removing sediment to keep the artery clear and prevent blockages. Through this fusion of advanced technology and meticulous human care, these passages can operate safely for decades, a lasting testament to engineering resilience in the harsh, unforgiving depths of the ocean. In the crushing dark, where light itself surrenders, humanity has carved its own horizons. Beneath the immense weight of the ocean, arteries of steel and concrete now pulse with human ingenuity. Each segment laid in this unforgiving world is far more than a triumph of engineering. It stands as a profound symbol of our courage and the relentless drive to push beyond every known boundary.